Okay, so I'm going to be talking about network verification, giving kind of an overview, and we have 2 sessions here. I think there's plenty of time, not planning on necessarily using all of the time, so keep it interactive, interrupt me with questions anytime. Let me start off by asking how many of you are pretty familiar with networking broadly? Okay, software-defined networking. Okay, few less. How many of you know something about network verification? You've read maybe one paper at least in the area. Okay, also many. How many of you know like comprehensively everything about network verification? All right. So, okay, so pretty experienced crowd. So I will try to go a little bit faster at the beginning, and we can save more time for questions and so on. So a little bit of context. So I am a professor at UIUC. I'm also co-founder of Veriflow, which is a startup we founded in the network verification space a few years ago that just came out of stealth mode last year and released our product late last year. I'm kind of spanning both worlds and can talk about it to some extent. So, all right, let's get right into it. So, at a high level, what we are doing here with network verification, the whole story is that networks have become very complex. They were simpler beasts where you put a packet in one end and it goes through the series of tubes and it comes out the other end and everybody is happy. That was great. And for a while that worked, and for a while longer we stuck with that model because you could just say, all right, don't touch it, it's working. I'm not going to change it, right? That becomes harder and harder as the network becomes more complex and as enterprises want to move more quickly in terms of changing and advancing what their network can do. So now we're at the point that it's just hard for humans to understand with any confidence what the network is doing. So let's automate. So automating in this case means the field of formal verification. So formal verification is the idea that you are taking a design and mathematically analyzing it to prove whether or not it has some property. Formal verification has been around for a long time, and it's been applied successfully to microprocessor design, to aerospace in various ways, to NASA's Mars rovers, so the flight software, aspects of the flight software are verified. So you might have seen the movie The Martian. Anybody see that movie? Okay, yes. So if you didn't, I'm not giving too much away that Matt Damon is stuck on Mars and at one point has to dust off the old rover and use it to communicate back home, and it actually works after many years. And of course it's a movie, but that's a little bit believable because those things are quite dependable and they last much longer than their lifespan, in part because of not only the hardware but also the software is so robust. So that's what we want to see happen for networks. That's the vision. What I'm planning to talk about today is, first of all, some background in networking. And this is the part I'll go a little bit more quickly over. And then we'll talk about data plane verification, configuration verification, and a little bit more deeper into these two, and then just kind of survey the research landscape of what's out there a little bit more broadly. And then at the end, some insight into network verification in the real world and in production, and lessons learned from that. So that's what we're going to talk about. Somewhere in here, we'll take a break in the middle, about halfway through. Okay, so let's get right into it. So background in networking. So many of you are probably coming from an academic context. This is a diagram of what a real-world enterprise network looks like. This is from Cisco's website. And it's showing kind of an overview, and even this is much simplified, of all of the multiple sites you've had. You would have different kinds of connectivity at different kinds of sites and at different kinds of layers. And each one of these would then split out into many more components if you zoomed into it. Like if we zoom into the data center, the data center architecture typically might look like something like this, with core routers and a aggregation layer, firewalls hanging off of that, an access layer, and then servers hanging off of this, and storage devices, and so on. And at each of these layers, there's different protocols that are involved. You might be using layer 2 at the access layer and below, at the aggregation layer, kind of translating between layer 2 and layer 3, and then the core routers are just running layer 3 IP. This would be kind of typical. But then, of course, you might augment this with a more modern leaf spine architecture for a data center. So there might be also a cluster there with a different architecture. And all of these things are integrated together. And then on top of that, you may have cloud networks that you're connecting to. You may have SDN in part of the network, but definitely not all of the network for typical enterprises. So that's kind of some of what's going on there. Now, each one of these components is running many different protocols. Okay, this is a list of protocols that are commonly encountered by Cisco certified network administrators. I took from that website there. And large set of protocols. Fundamentally, it's, as someone who's used to thinking about clean computer science design, this almost doesn't make sense because there aren't that many things that a network does. You want packets to get through or not get through, right? But there's a bit more than that. There's load balancing and optimization, and then there's a lot of sort of historical artifacts that have built up over time, right? There are many, many different protocols that basically do path selection in various different contexts, right? And resilience. You know all the routing protocols, BGP and OSPF and so on, but then there's other protocols to say, well, we need to have failover at layer 2 because that doesn't work very well with the routing protocol spanning tree that's used at layer 2 and so on, right? So there's more and more different protocols that come in to kind of, MacGyver the situation that we have into something that we want. Now, each one of these protocols then gets configured and have a lot of configuration options. And each of those, this is a very simplified, basic config for BGP and HSRP. And each of these configurations for the protocols is going to differ across vendors. Okay? So I just want to kind of give some illustration of how much complexity there is there. And after all that's done, that's the job of the human network architect and operator. And then these configuration files are fed to the devices which run device software. They might be running thousands of different RFC implementations. Those protocols communicate with each other and exchange routes and so on. And that produces a data plane state. So the data plane state are low-level rules that control the behavior of the device. So whenever a packet goes into the box, it's going to follow those rules to decide what to do with the packet. So if we zoom into one of these guys, it's basically, you can think of it as a little program in the data plane that has a format something like this. It might have a rule that says, okay, check if the port is 80, if so, not 80, so drop it. Otherwise, check if the IP address of the packet matches that prefix, if so, forward it, and so on. You'd have a long list of these rules. Matching packets according to certain fields and then taking actions. Okay? So you can think about the data plane of each device there as a little program. You can also think about the whole network as a big program that's taking in packets and computing how they should flow through the network in this distributed way. Okay? So today, how do people deal with this complexity and ensure that networks are actually operating correctly? Still, the number one method, and we actually did a survey on this at some point, is manual spot checking. Right? So if you make some change to the network, very often errors are associated with changes. You'll manually go to the service, make sure the service is still working by accessing it over HTTP or trace routing or pinging. Of course, that's not really getting you any guarantee, right? Because you may be at one point following a specific protocol to another point. What about all possible other sources and destinations that may be involved? And the second most common technique, also pervasive basically, is some sort of monitoring. In other words, wait until there's a problem and then catch it, right? So this is, for example, gathering headers of packets or samples of headers of packets with protocols like NetFlow and SFlow, and analyzing it in some way. And there's a broad space of this kind of analysis, and it's very useful and interesting, right? You can do performance analysis. You can run it through machine learning algorithms. There's dozens and dozens of companies doing this kind of thing, where you gather as much data from the network as you possibly can, as quickly as you possibly can, and stuff it into a machine learning algorithm, either something simple or something advanced, and look for anomalies in some way. Okay? So that can be useful, so particularly useful for monitoring performance of applications. But you're only, by definition, seeing problems after they're already affecting users. Or you're seeing vulnerabilities after they're already being exploited. Okay? So basically, what we want to do with verification is in some way get ahead of that. Right? So just to kind of put a bow around this is a survey from this paper in NSDI a couple years ago of network operators. 89% said they're never sure that their configuration changes are bug-free. 82% said that they're worried that changes would cause problems. And this is a bit hard to quantify, but I've seen numbers like 80% or more of outages are ultimately traced to human factors. Okay, now the other piece of this whole picture that I just want to bring up so we're all kind of level set here is software-defined networks. This is one of the answers to that whole space of network complexity. Let's get rid of all of the vertically integrated devices, the manual configuration, and say each of the devices in the network is going to have only a thin, open interface to the data plane that will be controlled by a logically centralized controller. On that logically centralized controller now will run applications that deal with higher level abstractions. Okay? This is hopefully a more programmatic, ultimately simpler way of managing the network. But it's software. It's still software. Software can still have bugs. And also in the foreseeable future, SDN is only going to be part of the network. And today it's very, very small parts of most networks, if it's used at all. Okay, so let's get to network verification. Maybe we can define it here. I took a crack at a definition. Network verification is the process of proving whether an abstraction of the network satisfies intended network-wide properties. So these words are important here. So network-wide, most of the work in this area is dealing with network-wide or end-to-end properties, rather than, let's say, a two-party state machine, right? And verifying properties of a protocol that's communicating between two devices. That's another area of work that's also interesting. But here we're dealing with thinking about the whole network as one system. And I think that's important because, again, this is part of the whole story of networks becoming more like a piece of software, right? So, and we'll talk a little bit more about that later. Okay, network-wide properties. So what properties may be of interest here? Any ideas? Somebody give me ideas. In the last talk we heard, I think a few. But what would you want to verify in your network?
No loops.
No loops in your network, yes. So there should definitely be no loops. Possibly no black holes, although some black holes, some packet loss is intentional.
Full connectivity or partial connectivity.
Partial connectivity, yep. Various levels of connectivity, and you'd have to be more specific to actually turn that into something you could verify.
Yes, isolation.
Isolation, maybe you have a PCI compliant zone in the data center. You don't want anything in or out. Yes? Yeah, that was it? Okay, good idea. Yes?
Policy enforcement.
Okay. Policy enforcement, like certain protocol, certain ports should be accessible or not accessible.
Also policy chaining.
Right, so service chaining, you have to, you enter the network, you have to go through a firewall and then a load balancer before you hit any database server. That being an example there. So these are some good ones. So just, I think we hit, some of the highlights here. You can also talk about a little bit more performance-oriented aspects, and we'll see a number of other examples of properties that you can check. So properties, invariance, or intent of the network operator, I'll use those words interchangeably. Okay? Now, the abstraction. Whenever we verify something, we need to be verifying a precisely defined model of it. Okay? So if we're talking about software verification, we have source code, and the source code is intended to be compiled in some language that has a spec. Okay? Now in a network, we've got to choose what level of abstraction we want to use for network verification. And I showed you that picture of this big complex network and all those interacting elements. We can kind of boil that down to a stack. There's a human written configuration that gets sent to control software that runs distributed routing protocols or runs an SDN controller. Even in SDN, you're going to have some level of human configuration. The output of that is data plane state, which is that's whatever is touched in the fast path when the packets are being processed by the system. And then that data plane state goes down to the actual packet processing hardware. Okay, so we could say, all right, the configuration, that is like, as an analogy of software verification, this is like our source code. Okay, so we're going to take the config, and we know sort of the language of that config, and we'll verify that. That's one way to think about this. But we could also say, I actually want to treat this like maybe this control software is my SDN controller. I might have written bugs in that. I want to verify all of that. Okay? Or I could just say, I've let this run. I want to look at the data plane state. That's the program that's running when packets are actually flowing through the network, right? So there's multiple levels here. Whoops. There's multiple levels here okay, I've got to go back one. There we go. I got the right part. Yes, I've got a loop in but fortunately only a finite loop. Okay. There's multiple levels of abstraction that we can model the network at. And basically these correspond to kind of what I'd say are the major categories of work in network verification. So we're going to take a look at a few of these. And you can probably already see there might be some trade-offs between them. Any ideas about that? Like where looking at information from one of these layers would give you something that another layer wouldn't.
Yeah. Maybe real time versus for all network events. If you're just verifying your data plane,
right.
You know what's happening now, but you may not know.
You may
different software packages.
That's right. So if you look at the configuration, you might be able to think about what could happen for many different data plane states, rather than the current data plane state that's there. That's one major difference. Okay, so we're about to dive into, I'm going to start with data plane, and then we'll kind of work our way up.
So Brighten, are you going to talk about, should we keep in mind the SDN model now, or are you going to talk about how one translates this horrible list of protocols you mentioned before, how it's mapped into these clean layers?
Yeah, so we're going to actually assume the horrible, ugly real world, unless otherwise specified. Yeah. Although most of the ugliness we'll save till later. Yes. But there is that horrible, ugly world. All right, so before we dive into data plane verification, any questions? Okay. All right, so data plane verification. So first let's talk about it as it relates to config verification. So we have this picture of what the network is doing there, kind of the control stack. If we did configuration verification, this would be the input, and we would have to predict everything that happens below, which means we need a precise model of what happens in all of that. Okay? Or you're only as accurate as what that model is. And remember, there's tens of millions of lines of vendor-specific code in this box. So the idea of data plane verification, so we're going to get to config, but we're starting with kind of the lower level thing, which is data plane verification. The idea is, well, what ultimately matters is what happens to your data flowing through your network. And the only thing you need to know for that, at least for a snapshot of the network, is the data plane state. So that philosophy is saying basically, let's verify the network as close as possible to its actual operating behavior. Okay? So the advantages, and we kind of already started to allude to this, this is something you can do that's insensitive to the control protocol, because you're kind of operating at a narrower waist of definition of what the network is doing. The data plane is inherently somewhat, at least somewhat narrower, because if for no other reason, it has to operate at line rate. It's going to be more accurate, because you don't care what happens on the higher levels. If there's some bug in an implementation of a control protocol, you'll see the results of that reflected in the data plane, right? If, let's say, you do a software update and the behavior changes slightly, you didn't change the config, but when you updated to the next version of your router OS, something changed, right? You'll see that reflected in the data plane state. So, high accuracy, but only checks current snapshot of the network, right? So it's still predictive in the sense of you're not waiting for traffic to flow through the network. We're going to look at the data plane and basically predict all possible traffic behavior that could happen, but it's not predicting what will happen to changes to the data plane state. Okay? So, do we need accuracy? One of the things that we looked at in our Anteater paper was a sample of 78 bugs randomly chosen from the Quagga repository, the Bugzilla repository for Quagga, which is this fairly popular open source software router. So of those 78 bugs, so again, these are bugs, so none of them you would see by looking at the config. You could only see it looking at a lower level. And even then, it may or may not manifest in the data plane. Of those, 67 could cause a data plane effect. Some examples, under heavy load, in some cases it would fail to update the kernel's routing tables. So inside the router, it had a notion of what the route's for, but that didn't make it down into the kernel in all cases. And imagine how hard that would be to debug, right? Where the config is right, Quagga is telling you it's right, and the data is not flowing. What's going on, right? In some cases, BGP sessions could remain active for longer than they should, which could then leave routes active or the wrong routes. 11 of these did not affect the data plane. An example of that was the management terminal hangs when you run show IP BGP in some cases. Okay, so arguably if it doesn't affect the data plane ever, then you don't care about it as much. It's not as critical. But the point is that this is one aspect of getting that accuracy, is that there is there are bugs in the software, but also there's a lot of other real-world aspects of what's going on in the network, right? There's flaky hardware, things going up and down. You might want to have some awareness of counters and things like that. There's interfaces that may not be specified in the config file and so on. So, okay. So that's kind of why you would want to do data plane verification. Let's look at the architecture for how you do this. So we've got the network, the physical network, with the data plane state, which are basically these tables of, under these conditions, match the packet that has these header characteristics, and if it does, then perform this action. Okay? So the verifier basically takes two inputs. It needs to know what the reality of the network is and the intent that it's supposed to verify. Like, for example, can any packet starting at A reach B? Very simple question. And then we'll have some sort of diagnosis. We'll say either, yep, that always happens, that can happen, here's an example, or no, it can never happen. Okay. So in doing this, we're going to run into a computational problem, of course, which is like, formal verification. Broadly speaking, there's a lot of possibilities here, right? A lot of cases that we need to check to really be able to prove that a property exists or not. So, how many possible behaviors are there? And remember, we've already restricted ourselves to, we just want to understand the present data plane. Okay? So the number of theoretical packets is going to be 2 to the number of header bits times the number of injection points. Okay? So even if we only care about your Ethernet and IPv4 headers, this works to out to about 3 times 10 to the 95 possible packets. Okay? And any of those differences could matter depending on how the network is behaving, right? So that's 10 to the 95, just comparison points. There's the estimated number of atoms in the universe, 10 to the 80, and number of grams of salt in the Dead Sea is about 10 to the 15. So a large number. So we're going to have to do some more efficient calculation rather than running through all possibilities, obviously. So let's digress a little bit into the complexity of this problem, right? And of course, in the general case, formal verification is like the holy grail of computer science. Tell me if my program crashes or not, which is, of course, undecidable. But we're talking about networking here, right? And we're going to use the domain to our advantage. So let's start with a very simple question. Let's say all the data plane does at each device is IP longest prefix match, meaning there's one field that you care about, the IP address. Okay? We'll just start with this. See, is this case, how hard is this? So we have one field we care about. The rules are going to be matching some prefix and giving an action, forward or drop. Okay? So, and the query is, can A reach B? So I'll give you 3 choices. Is this problem polynomial time, NP complete, or undecidable for this case? So let's think about that for a couple seconds. Is the question clear?
Well, what's the n? The n is the number of nodes in the network, or what's the n? The routing table, the global routing table.
Yes. So imagine that the packet header length can grow. Otherwise, it's not very interesting. And n is the size of the input. So the input is the topology of the network and all of the forwarding tables.
Probably incomplete.
Let's vote. Polynomial time? NP complete, and undecidable. Okay, so all right, it's one of those two. Yeah, this is in fact polynomial time. Okay, and we'll talk about why in just a moment. Next question, what if we say it's not IP longest prefix match, it's actually matching any range? Think about that case. Okay, I won't have you vote on that one. Next one, how about if we also allow an arbitrary bit mask? Okay, so now this says it's not necessarily just a prefix. I can look at one bit in the packet header and say, if bit 7 is 0, I'm going to drop the packet. Okay, that's all I can do. So very simple packet filtering, right? Like the most simple that you can imagine. All right, so for this case, let's vote. Polynomial, NP complete, or undecidable. Polynomial?
Could you explain that again? So when you say we also allow this as an arbitrary...
So we can have an arbitrary network topology in all of these cases. Okay. What a node can do in the topology is its forwarding rules have to satisfy these constraints. Here the constraint is just IP longest prefix match. Here you can look at, imagine it's still one field. Any position in that field maybe not starting from the beginning. And I can forward or not based on the value of the bit in that field.
But you know that. It's not that it's unknown. Like
Right.
you extract the IP longest prefix match table, you can extract the arbitrary bitmask from the node. It's not an unknown.
I know exactly what the node, yes, right. So the input here is going to be something like, node 15, rule number 1 is, drop the packet if bit 7 is 0.
Okay.
Dot, dot, dot. So this is in essence your network description, right?
Yes, that's right.
how you describe the network. That's
Yes, and I'm putting restrictions here,
Okay,
increasing on the input.
Okay.
That's right. So did we vote on this yet? Polynomial time, NP complete, or undecidable? Okay, I think you guys thought this one was easier than the other one, on average. Okay, that one's NP complete. Let's say we also allow stateful devices. That means when a packet goes through the box can modify its internal state and do something different to subsequent packets. Example of when that happens? Anybody? Firewalls, yes. So you send a flow going outward. Only after that happens can the flow coming in the reverse for that port enter. Okay, so this one might be a little more clear, but polynomial time, NP complete, or undecidable? Yes, okay. Well, in general, it's undecidable, but you're all right there because actually you have to be a little bit more specific on what state and so on. And so this has been analyzed. You can look at this paper, and it depends on your assumptions there. But it can be pretty bad, obviously. Not too surprising. Okay, let me just quickly give some intuition for what's going on here. I'm going to use the whiteboard, I think, for the first time in this workshop. Let's see. Hopefully this is visible on the camera. Is it better if I'm on this side? Whatever? Okay. Let's start with that top case. So imagine that I collect all of the IP forwarding rules from the entire network. Okay? I'm just going to put them in a big bag. And this is my IP address space. Okay? So this is 0.0.0.0, and up here is, 255.255.255.255. Okay? So I'm going to take all of the rules and go through them one by one. And actually, the following is going to work if I'm dealing with prefixes or arbitrary ranges. So it doesn't necessarily have to be on these power of 2 boundaries. So you might have ranges if it's like, you're talking about ports on a certain range. But I do have only one field that I'm dealing with. So I go through the rules. Okay? Take the first rule. what does the first rule do? Maybe it falls here. It's saying if the packet lies in that space, then forward it in some way. So I'm going to remember that these boundaries matter, which is to say that something different can happen somewhere in the network if your packet falls in this group versus this group versus this group. Okay? That's the first rule. Now take the second rule. The second rule maybe is over here. Okay? Again, I remember the boundaries. Maybe the next rule falls here. Okay? Now this is interesting. That rule falls there. All of these packets, same thing happens to them as before. No change. These packets, same things happens to them as before, but now actually something different may happen over here than happens over there. These packets, still the same thing, they're all going to be grouped together, right? They're in an equivalence class. Because, they're matching the exact same sets of rules. This group here now gets split. Okay, so I have to remember the split points. So every time I take one of those rules, that's what I do. I remember where the boundaries are. And thank you. So every time I do that, how many more splits are there? Where a split is taking a range of packets and it's saying, this range is no longer equivalent. I've got to divide it up. It may be treated differently somewhere in the network. Every time I add one of those rules, how many more equivalence classes do I add? At most 2. So the total number of equivalence classes is at most twice the number of rules. So there's a linear number of equivalence classes. So basically what I can do now is I could go through each one of those. And I only have to analyze reachability, just a graph traversal through the network once for each one of those. Make sense? So that's polynomial time, that question of reachability. OK, let's take the arbitrary bitmask case. So again, I'm trying to get from A to B, and I get to construct a network, right? I get to construct a annoying network to show that it's NP complete. Here's the network I'm going to construct. Okay, left to right. It's always going to have 3 different links from one stage to the next stage. Okay, and I'm going to have potentially many stages end to end in this network. All right, and my packet, remember, I can think about this as an array of bits. So just think about that as a vector there from 0 to n. And let's say I'm given the forwarding rules that this particular link will forward the packet exactly when the bit number 4 is 1. Otherwise, it's dropped along that link. This guy here says it's going to forward when x7 is 1. Last one's going to forward when x1 is 0. Okay? So if we wrote this in logic terms, when does the packet somehow proceed from the 0th stage there to the next stage? It's when x4 or x7 or not x1. Okay. Now, that's for the first stage, and it needs to also pass the next stage and the next stage and the next stage. Okay. So you probably recognize this format here. This is 3-sat. So you can give me any 3-sat formula, and I can build a network that exactly corresponds to that formula. Make sense? Okay. So I have just solved 3-sat with this network, just with, annoyingly, 1-bit packet filters is all it takes to make it really annoying. That's NP complete. Now, the hope is that in practice, it's not going to be that evil. But yes, that's the question.
That's what I was gonna ask.
Yes, we just have to cross our fingers. Other questions? So with that in mind, the first work that my group kind of forayed into this area was called Anteater. And the idea, this paper, the contribution was basically introducing data plane verification as an architecture in terms of why you would want to do it and the trade-offs, and building the first system that verified a real network. And the way we did that was to say, okay, let us express the data plane in a general way where we can reduce it to a SAT formula and then plug it into SAT solvers that are getting better and better. And then we'll check it with an off-the-shelf solver. Let's see a little bit about how we can do that, because I think it's interesting to kind of compare different techniques for representing the network. Ultimately, there's now about a dozen different network verifiers, and they're all, in a way, ultimately doing a similar thing, but in very different ways. So this is the first example here. So what we'll say first is kind of like what we saw in the previous slide, where we were thinking about complexity. We're going to say a packet can flow over an edge from U to V if and only if it satisfies some formula, PUV. Okay? Like, for example, IP longest prefix match. You know, this is going to say, all right, your destination IP has to be in that range. And I'm writing this at a higher level in terms of IP rules, but obviously you boil that down to boolean variables over the bits of the packet header. Okay? So now reachability becomes SAT solving. So if you want to reach from U to W, in that particular network there, you need PUV and PVW to be satisfiable, that formula. So you could plug that into the solver. Now the next problem is that there could be exponentially many paths. So if you're looking at a particular path, you just take the and of everything. But if you want to compute reachability and n, there may be many, many different paths. Okay, so for this you can use dynamic programming, also known as loop unrolling in this case. So this is kind of a known general strategy in verification. So a way to think about that is what are the intermediate variables? Can you reach x in k hops is the intermediate variable. And then you write the k plus first in terms of the previous ones. Okay? So now it's no longer an exponential number of constraints and variables. So this is a little similar to this other paper that I'll mention later when we kind of talk about the overview. Now the next problem here is transformations to packets. Because the packet, as it flows through the network, doesn't remain a static set of variables. There's lots of ways in which the packet is modified. Okay? We talked a minute ago about a middle box, like a firewall, modifying its own internal state. Okay? And we're not dealing with that yet, just to be clear. Okay? But the packet itself can be modified. How can the packet be modified? What's an example? The NAT rewrites your address field. What else? Encapsulation. So you tunnel. You might go into a GRE tunnel or a VXLAN tunnel or an MPLS tunnel. Anything else? The hop count is modified. Yep. And we're choosing not to model the hop count because that's annoying. It adds more. It adds more complexity to modding with basically limited payoff. But another way in which the packet is modified is every time you go from one layer 3 device to another layer 3 device, your layer 2 addresses are modified. So it's always happening, right?
How do you capture loops if you don't model the TTL?
So in that case, it would be an infinite loop. So in the real world, there are no infinite loops because the TTL decrements and then you ultimately are dropped. So the analysis will say, oh, you have an infinite loop. So it's a pretty good approximation of reality. And of course, you're not going to really want any such infinite loops, so you don't really care about the distinction generally between being dropped after the 254th versus 255th hop or something like that. Okay, so the way that we dealt with packet transformation in Anteater was to say, let's take this example of tagging the packet. It's going to now transit this edge if let's say the MPLS label is 5. So that, I don't know if you know how many of you know what MPLS is? Okay, almost everybody. It's a protocol that has a field. And that field gets slapped onto the front, and it tells you which path you want to go down. So some other label might send you in a different direction, but the way that you go this way is if your label is 5. Okay, so, and that tagging with putting 5 on the front is going to happen at this device. So what we do is we model the history of packets. So rather than a single packet, we now have a vector of variables, okay, which is the packet's history across time. And now you can think about it again as sort of variables that aren't modified. A transformation then is going to be a constraint over successive adjacent versions of the packet header. So in this case, the constraint is going to be that the IP destination of version I, what we want to say is if it's in here, then it also has to satisfy the next hop constraint if it's going to pass through there. Okay? So what that's saying is packets which start out in, say, version 4 with this header, and if it's modified to have the label in the next version, version 5, then it will in fact pass from there to there.
But you didn't describe how, what the rule to convert to this label 5 is. So you may get to a conclusion that the packet can go from U to W, but actually there aren't any packets that are labeled 5 if they cross V.
Let's see. So this is one of the constraints that's saying, so this isn't a complete description. Yep. But it's one of the constraints that is saying that if this is in there, then such packets are going to be allowed through. But if you have a different label, so there will be a different rule for a different label, right? And that rule might just say drop, right? So there wouldn't be, this formula would not be constructed to represent passing from U to W. What I'm showing here is the formula that you end up constructing to represent passing from U to W, if that makes sense. Okay. But you'd have a similar rule for whatever V is doing. So you have to look at what V is doing to produce these rules. Okay. So whatever that, maybe this is actually what's answering your question. Whatever that function, that transformation function is at that node, you put in those constraints. Okay. All right. So we built this and we tried it out. And I can't say it was extremely fast, but it worked. And we tried it on a real network of about 178 routers, supporting over 70,000 machines. And this had a variety of different control protocols in it, OSPF, BGP, static routing. Experimented with several different invariants or properties that we were checking for. So loops, packet loss, in other words, falling into a black hole, and consistency, meaning there's a pair of routers that you want to have the same behavior. So it's not saying what that router is supposed to do. It's just saying it should be the same as some other router. And that's useful because maybe you don't know exactly what it is supposed to do, but we can look at the network and say, okay, these are two core routers. They're supposed to do the same thing, I know. Even though that I wasn't the one that built the network, I can look at the network and say that, and I can perhaps find problems that way. So consistency checking is a powerful thing in general. A number of bugs were revealed, including loops. We can, just a few examples of how these happened. So in this network, there were actually loops on the core routers that were externally accessible by anyone on the internet, which means that if someone malicious knew about that, they could send a stream of traffic to those routers, and whatever volume they sent in would be magnified by over a factor of 200, so they could very easily take down links. But what happened there was the architecture of the network was there was the backbone, bunch of other devices I'm hiding. It went to an intrusion detection device that went to then a building. When that IDP started getting overloaded, the operators decided to set up a bypass, and certain traffic that could be basically whitelisted so that you wouldn't have to overload the IDP. So traffic to YouTube. All right, we know it's YouTube. It's a huge volume. It's actually maybe most of the volume. We don't need to be inspecting that. So that was set up with a static route that interfered with the dynamic routing used in OSPF. And so for the certain prefix, it introduced a number of loops. A few others, there was packet loss that was blocking some compromised, that formerly compromised machines, but it had been in there for over 5 years, so it was stale. It should have been taken out. Consistency checking revealed management interface that was exposed more on one device than another, so that's a security risk. So those were real problems that were revealed there. Any questions about Anteater? So that's an example design of a data plane verifier. Now we're going to bump it up a level and talk about real-time verification. Again, just to set the pace here, who's familiar already with a real-time data plane verifier? There's several out there now. Okay, most people are not. All right, how are we doing on time? When were we supposed to end the first segment, Michael?
After an hour, so roughly now.
Roughly now?
Yeah.
Okay. All right.
1 hour segments.
Yeah. Okay. So let's take a break now. Any other questions?
This is an empirical question. So you feed this into a SAT solver,
Yes.
right, and it works. Is there a reason to think that for whatever reason, when you translate actual forwarding rules to these Boolean formulas, you get a particularly clean structure? Is there any reason why the SAT solver works that we can account for?
Well, I think one reason can be looking at the result that if you're only dealing with IP, actually, it's not that hard of a problem. And so most of what the network is doing is not that complicated. Okay, there's a spectrum. Okay, so I don't know in particular that there's some special structures that are particular to a SAT solver, but let's ask the question in general, what level of complexity is there? How much structure is there to be exploited?
If you were to remove the SAT solver and just
Right.
tackle this
With some other heuristic or some other algorithm, yeah. There's a spectrum, right, of complexity, between like easy for a human, harder for a human, impossible for a human, easy for a computer, and harder and harder, and then like full program verification, right? So we're somewhere in the middle there, where the complexity is, it's too many possibilities for a human to deal with, but it's okay for a computer. So you could say, all right, one way to measure that would be the number of equivalence classes, and we'll get to this when we talk about the next the next design here, but how many distinct behaviors should there be in the network? If there's an exponential number of distinct behaviors, that's kind of odd. It's like, why are there that many different traffic classes? There shouldn't usually be. There's a lot of things that you want the network to do. There's a lot of different destinations. Some of the rules for those destinations might be complex, but the number of distinct behaviors shouldn't be that large. So that's one way to kind of break it down. Number of distinct behaviors, and then there's a question of the complexity of representing a single behavior. And that might be a little tricky, but that's the best I can do.
So in a cluster, in a data center that supports significantly high different parallel paths,
Yes.
isn't it going to introduce extra complexity to your formulation in SAT? So the number of hops is small, but there are so many parallels.
Yeah. That's a good question. So it would, I wonder if the dynamic programming would end up picking up that structure. That's one. The other part of that is what level of detail that you model. And in a data center in particular, you have many paths, and which packets go down a particular path is actually determined by a hash function.
Yeah.
You probably don't want to model a hash function, right? So a much simpler way to model that is to say that any traffic may go along any one of these links. So you're modeling some uncertainty. And so that simplifies the problem also. You still may have a lot of paths.
Okay, so you're describing a different property that you want to. Okay, but so you basically, your claim about using hash functions means that you want to claim the property that any packet is going to visit the first tier, and then the second tier, and then the third tier, and this is how you prove that it reaches the destination.
Yeah, I mean, ultimately you want to check some property that maybe involves reachability. And you want to, I think, for most of what we're talking here, you want to be able to describe and prove any property related to data flow at some level of abstraction. So there's some art to picking the right level of abstraction. And just giving some examples here, TTL and hash functions fall outside of the line of what you want to model. Yeah, but where it would really a lot of actual behaviors, different behaviors would happen, would be if you have that very rich network with many different paths, and you have enabled source routing, where you can actually use maybe even very weird paths that backtrack for a little bit and then keep going, and you really do have an exponentially large number of distinct behaviors. And so that's a good thing to think about. I haven't seen published papers that have F10 would be a system that does that kind of thing, yeah. Or segment routing, it has some aspects of that, which is a protocol that's getting some attention now. So it may come up. It's been, I think, not, because it's not really used in practice today, hasn't been a focus of any of the verification published work that I've seen. Okay, let's break there. Thank you.
Continue in 10 minutes.